Any questions? Okay, so let me comment on one of the questions that some of you raised. And it's again related to this. And the question was, if I want to try and make an explicit example where this condition is met, by using the states that I have introduced as in the explicit way, like the tachyon and the massless states, it seems impossible, right? Because the tachyon looked like that. The vectors looked like this. And all of them were by construction having a -1 at the final, in the final entry. And this is because all these states had this form, e to the -5. Right? So how can I may have a non-zero amplitude? Right? Even an amplitude between three vectors. Right? Am I proving too much? Am I proving that all amplitudes are 0? So the answer to that is encoded in this second bit. Right? So what you can do is to use the second bit of the vertex operator to construct another representative of the same object that has the same BRST property, so is annihilated by the BRST charge. Right. I will not give the construction explicitly, but let me just say kind of conceptually how it works. So you would take this object here, and you don't need to dress with e to the -5. Now, okay, that's not the full version, but that's the bit which I need. So what I'm saying is that you can have another representative of the tachyon state that looks more like this. So this second representative, you see, you can combine with those like this to see, to saturate the super ghost anomaly, to have that. So people call these different representative pictures. Right? So you have one vertex, one state. You can have a vertex operator describing the emission of that state in one picture, another picture, so on and so forth. So what is this picture? The picture is the eigenstate of this operator. So it's something that is counted by the zero mod of, by the super ghost, sorry. Right. So you see that if you act with this guy on those objects e to the -5, well, then you would get 1, right? The coefficient of the simple pole is 1. So people say -1, whatever. These people would say, yeah, that picture is picture -1. It captures this coefficient here. The other state that comes from, that is constructed from here and corresponds to this lattice point will have h6 equals 0. And so when you act with this object, it will give no simple pole. And so it will be in the picture 0. Right. So let me just say in words, there is another way of finding these different pictures. Right. You can start from your -1 picture, the one that I was defining explicitly there, right? And then do the following trick. You take your state in the -1 picture, so for instance, e to the minus phi e to the ikx c. And then you do something which is forbidden. You multiply it by xi. Why is this forbidden? Well, because I am using a field which includes the zero mode of xi, and as you see there, the zero mode of xi is outside the original description in terms of beta gamma. So this is something that has no corresponding expression in beta gamma. So you do that. Notice that this xi has conformal weight 0, so multiplying by xi does not change the conformal weight of this state. So you take this, and then you do the anti-commutator with the BRST charge. Right? When you do this anti-commutator with the BRST charge, you would say, okay, this is a BRST exact state, right? Because I get it with the commutator of the BRST charge, right? And that's true, but that's true in the large Hilbert space. So what you do, you say, okay, if I take this result and then interpret this result in the small Hilbert space, the one where this psi is gone, then that object is not BRST exact. And the result of this calculation is this other representative. Gives you an explicit expression of this other representative. So people call this operation picture changing. And you immediately see, right, from that form of the Qs, you see that Qs contains gamma, and gamma contains e to the phi eta. Right? So when you do this calculation, basically you are increasing the value of this thing, of e to the phi. Right? There was -1, and this Q will bring 1 and more. So this is bringing you up in the pictures, and so it will connect that expression that is in the picture -1 to the corresponding expression, this one, which is built from the zeta, the Greek zeta term, which is in the picture 0. So this is another thing which makes the superstring a bit fiddly, baroque, that when you write your amplitude, you need to make sure to saturate this, right? While it was very easy to do the corresponding task for the bosonic theory, just choose 3 operators with C and integrate over all the others, here you have to choose the operators in different pictures. But it's an algorithmic calculation, right? You have just one representative in picture -1, one representative in picture 0. In particular, at 3 level, everything is super well defined and explicit. And you just choose the right number of picture -1 and picture 0 object to get something that saturates this. So if you do that for this even, odd, right, you will choose like the 2 massless state in this picture, the massive state in this picture, right? So you saturate the -2, but then you will see, I mean, this is the general argument, but you can recheck in this example that you are not able to satisfy all these conditions. Right, so that is 0. Very good. So let me now go back to space-time, right? And try to introduce the Raman sector. Okay, the Raman sector is the worksheet, but then introduce the Raman sector and then define for you what the spectrum of the superstring theory is. Right. So why did I claim that this bosonized language gives me a nice, easy way to introduce the Raman sector? Well, because now I can think about the Raman sector as extra points in this lattice. And these extra points are just the set of points that are at half integer, that have half integer value. So I'm now allowing HA equal to be plus or minus R, and H phi the same, where R is in Z plus 1 half. So example, I'm considering states of the type e to the IH, H1, H2, H3, H4, H5 minus phi over 2. So just add new points, and the key information is that these points have to have half integer values for all the bosons. So you are not allowed to have just e to the IH1. You are not allowed to have, for this vector, 1 half and all zeros. You have to have all of them half integer. Is this clear? Yeah, so what I'm saying is that you have this 6-dimensional lattice. The lattice was made out of the points that have integer coordinates. Now I'm adding new points. These new points have half integer values for the coordinates, but they must be all half integer. Right. So you are not allowed 1 half 0, 0, 0, 0. 0 is like an integer number, right? So they have to be all half integers. So they can be like 1 half, 1 half, 1 half, 1 half, 1 half, minus 1 half. Or they can be 1 half, 1 half, 1 half, minus 1 half, 1 half, minus 1 half. And then you have a new set of points in your lattice, right? Infinite new number of states. Now, the interesting information is that if you now take one state like this one, so this is inserted in zeta 1. So on your worksheet, you have zeta 1. Right. That state is inserted there. And now you take a fundamental field, psi, and you insert this psi somewhere else. Now you can calculate the OPE between these two objects. Right. And here you have this psi is some e to the plus or minus IH. I don't know, IH1. And this is in Z. And then e to the I2, some HA minus 5. So this is this OPE, this is psi. And this is one of these new states that are defined by the half integer lattice point. You see, you can do the OPE now by using free fields. That's the power of this bosonized language, right? The only contribution comes when this guy H1 is contracted with this guy H1. And so this guy will be z minus z1 to the plus or minus 1/2. Right. So these H are bosons. Their contraction is just the log. So it's exponential of the log. And the power is just the number here times the number here. Right? 1 times 1/2 is 1/2. So I just want that you to stress again that I'm doing exactly the same calculation that I've been doing for the 3-point function of the bosonic theory, the 4-point function, right? Just taking the OP between these composite operators, right? Now you see that the point is that this is half integer. So if you take psi z and you go around the insertion of one of these objects, right? So this is basically saying z minus z1 goes to e to the 2 pi I z minus z1, right? I'm going around this. This product changes sign, right? Because of the square root. So this shows that these half integer weights are boundary changing conditions for the fermions and the beta gamma. So these objects are called spin fields, and people for many years were kind of struggling to calculate explicit in terms of spin fields. And it became just much easier when this language of bosonization was used, because then it's a free theory. And the example I did for H1, it works for H2, H3, H4, H5. So what I'm saying is that these fields, these operators, if now I can check that they are BRST invariant, will be the physical operators that correspond to the Raman sector states. And in these Raman sector states, I will implement the very same GSO condition. So I will implement a condition which says the sum of all H is even. So for instance, this one would be good, right? Because it's 1/2 plus 1/2 plus 1/2 plus 1/2, which is 1/2 times 4 is 2. And then 1/2 minus 1/2, they cancel. So this one would be okay. But this one, would be killed because is 6 times minus 1/2, which is minus 3. So this does not satisfy this, it's odd. So what I'm saying is, okay, I do exactly the same thing. I enlarge the lattice to all possible Ramon states, all the points that have half integer coordinates. And then I impose the same GSO condition. The sum of the weights has to be even. This tells me that this proof will work also in the Raman sector. Right? Here, the only information I used was parity on the sum of the weights. The same derivation will tell me that if I choose an even state in the Ramon sector, an even state in the Ramon sector, this correlator even, even, odd is 0. Very good. So let me just, I mean, you can do the calculation because in this Bosonized language, everything is free theory. Let me just tell you the result. So what you can do, you can take that BRST charge over there, write all the gamma in terms of the Bosonized language, do the OPE between those objects and these new states, and then you want to check that there is no simple pole, right? That's checking that the state is BRST closed. And if you want to do this calculation, which is kind of not more difficult than the bosonic ones, let me just tell you a hint. The most interesting bit comes from this part, from Q1. So maybe just do that. And you will get a condition that is linear in the momentum, right? So the vertex will be, the full vertex will be this one times C times e to the I kx, right? So this is the standard thing we had also in the bosonic theory, right? This is the new structure in the psi and the super ghost sector, right? So you can take that Q1, you can do the OP, you can look at the simple pole, and you immediately see that you get a condition, a simple pole that is linear in H, because it comes from the contraction of this delta x here. It comes with this x here, it gives a simple pole, right? So it's linear in H. So what I want to do now is interpret that constraint, right? That constraint will be some physical constraint, and as we did for the bosonic theory, we want to interpret that as some equation of motion, some free equation of motion. For the scalar, was just k square equal minus m square. Right? So what is it now? Okay, in order to do this, to interpret this, I need to tell you a bit more about these states. First of all, how many states of this type you have? The kind of the basic possible choice is to choose this to be either plus 1/2 or minus 1/2. It's kind of intuitive that if you increase this, you will get massive string states, more and more excited string states. So let me start with the choice HA equal plus or minus 1/2. How many possibilities you have? Well, you have 5 objects. So you have 2 to the 5, 32 objects. So you have 32 possible states, right? And their difference is just changing signs here. And this 32 splits into 16 that are GSO even, right? 16 objects like this one, where this sums is even, and 16 objects like this one, where the sum is odd. Now, if you think, okay, another calculation, okay, let me just say one more ingredient. So if you start from the Q0 bit, that's kind of the standard one, and you check that that term does not provide a simple pole, and you do it on this state, you will find y equals 0. So all these 32 states are massless states. So they look on the same footing as these ones. So if you try and give a space-time interpretation of these 32 states, right? Here we had 8 physical states, d minus 2 physical states, and we interpreted all of them as forming a space-time vector, right? The d minus 2 polarization of a massless vector. Now you can ask the same question is, what this collection of massless states that come from the Raman sector, what is the interpretation from the space-time point of view? We derive them from the worksheet. There are 32 states, they are massless, but what is their interpretation? They have to form some representation of the space-time Lorentz group. This representation is not entirely obvious in this language because we broke the Lorentz representation, the Lorentz group, into U1, 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 right? So we broke the Lorentz group when we paired the psi's to form this H. So that's why it's not entirely obvious. But do you know any representation that has dimension 32 of the Lorentz group? The Spinor, right? So if you have SO1, 9, right, the representation, the Spinor representation, and so this is total dimension 10, Spinor representation is 2 to the d minus 2, so this is 2 to the 5. So already just looking at the dimension of the representation, this tells you that it's a Spinor. And if you think about spinors, as I do in a very naive way, in higher dimension, as just tensor product of spinors constructed in 2 dimension and then in 2 dimension, this is an explicit representation that follows that. So if you look at how spinors are constructed in Appendix B of the book of Polchinski, that's just a mathematical construction that is mirrored by this bosonized language. Just want to mention that. But let me not enter into too much details. What I want to say is that we can also interpret the split between 16 plus 16. Right? This 32-dimensional representation, if you have a general Dirac spinor, splits into 2 Weyl spinors of opposite chirality. And the Weyl spinor would have dimensions 16 and 16. 16 complex and 16 complex. So this is something that you often see. The GSO projection in the Ramon sector is nothing else than a chirality projection. You just take the chiral or the anti-chiral. Here I'm just making this link. The spinors of SO1, 9 are very nice because you can have even a smaller representation. And that smaller representation satisfies the condition of Majorana and Weyl at the same time. So you do have just 16 real components. Now, the spinors you get in this form are Majorana Weyl. And you can see very easily in this language, just by taking the complex conjugate of this guy, right? And remembering that the 5th bit was a bit funny. The 5th bit was psi 0 plus psi 9 equals e to the I h5. So this is telling me that if I take the dagger of this, these psi's are real. If I take the dagger of this, h5 dagger is equal to minus h5. All the other are Hermitian. This one is anti-Hermitian. So what I'm saying is that if you take the dagger of this representation, the first 4 will change sign. This one stays the same, this one stays the same. So you see that the conjugate of this guy is still a state that is in the set of physical state, because you change sign to 4. And so you still satisfy this condition. Okay, so this is just a comment to say that the reality of the Spinor psi tell you that these 16 objects we are constructing are Majorana-Weil fermion. It really comes out from the CFT description. It's not, you cannot choose. Very good. So, any question on this technology? Otherwise, I describe for you the spectrum of 3 theories, focusing on the massless spectrum here in the case of the superstring. And the theories I will be focusing are type 2b, type 2a, and the open string for the D3 brane. Okay, so let me do it. Okay, so let me start from type 2 theories. So type 2 theories are the most natural generalization of what we did for the bosonic theory. So you just take your holomorphic part, you define physical state for the holomorphic part, then you repeat the same calculation for the anti-holomorphic part, and then you pair these 2 parts by satisfying the level matching condition. What makes the difference between type 2b and type 2a is how the GSO projection, so this projection that kills half of the state, is implemented in the Raman sector. So the Knavish-Schwarz sector, how it is implemented in the Ramon sector. So when I focus on the Knavish-Schwarz sector, and I focus on the Knavish-Schwarz sector both for the holomorphic and the anti-holomorphic part, I get the same spectrum. So type 2 theories will have a left and a right, holomorphic and anti-holomorphic. I can pair them as I wish. And so I can pair something from Knavish-Schwarz with something with Knavish-Schwarz, something from Knavish-Schwarz with something with Ramon, something from Ramon, something from Knavish-Schwarz, and something from Ramon, and something from Ramon. The only constraint I have is that these 2 objects, the operator, the state I have here, and the state I have here, the only constraint is that these 2 states have to have the same level, right? Level matching. So this is exactly what I did in the bosonic theory, but now, separately, each of these ingredients can be either coming from the Knavish-Schwarz sector or from the Ramon sector. The difference between 2b and 2a will be here, here, and here. And this is common. The common sector is just taking one of these massless state. I cannot take the tachyon because that's projected away by the GSO. So I take one of these massless states for the left sector and one of the massless states for the right sector. And so I get exactly the same content as the bosonic theory. Right? So the Knavish-Schwarz will have a massless vertex operator that looks like C e to the minus phi psi m, and then C tilde e to the minus phi tilde psi tilde n e to the ikx gmn with k square equals 0, k dot g equal g dot k equals 0. Right? So I take the left bit, which is written up there, the right bit, which is written like up there, and then these are the physical conditions. This is for the left sector, this is for the right sector, massless states. And so we, as in the bosonic theory, you can decompose this general matrix in a reducible representation, and you have a graviton, an anti-symmetric tensor, and a dilaton. So summary, the spectrum content is G mu nu graviton, B mn Kalb-Ramon field, anti-symmetric field, and phi the dilaton. Now, if you do the Knavish-Schwarz-Ramon sector, right, so what you do is you take one bit in the Knavish-Schwarz sector, and then one bit in this fermionic sector, and let me give a name, a collective name, to the 16 possibilities of I have here, and I call this as A minus 1/2. So just like, let me explain what the rationale is for these names. This minus 1/2 takes care of this ghost number. Right? It's just telling me the value of H6. And this big index A is a Spinor index in the Majorana Weyl representation of SO1,9. Right? So this is an index that goes from 1 to 16, right? And just goes over the 16 possibilities of plus and minuses such that the GSO condition is preserved. So you can start from this choice, and then you can flip pairwise signs. You get 16 different states, and I collectively call these 16 different states, I label them by this index. Okay. So this is what you would get in the Knavish-Schwarz-Ramon sector. And now, what is the analog of this polarization object, so the thing that is saturated with the free indices? Well, it's an object that has a vector index and has a spinor index. Now, what is an object that has a vector index and a spinor index in the space-time? It's not a vector, it's not a graviton, it's a gravitino. Now, if you do the calculation with the Q1, and you check the BRST invariance for the bit coming from the Q1, on a state like this, you will get the equation of motion of a free gravitino. So there is still this idea that the BRST invariance provides the equation of motion, exactly as it happened for the Navier-Schwarz sector. So finally, this construction provides you with fermions. Right? The Gravitino is a space-time fermion. You can write the Ramon-Navier-Schwarz sector. Well, you would just swap these two. If you do that, if you just say that the Ramon-Navier-Schwarz sector is just swapping these two, then you get the type 2b. And so you get another Gravitino. One Gravitino for the Navier-Schwarz-Ramon sector and one Gravitino from the Ramon-Navier-Schwarz sector. And the second Gravitino you have is just an identical copy of the first Gravitino. So let me call this Gravitino 1 and this Gravitino 2. So this shows that these type 2 theories, that's where the name 2 comes, have an extended supersymmetry in 10 dimensions. And this extended supersymmetry, people in the jargon call it n equal 2, 0. Because it tells you you have two Gravitinos, but they look the same. So these two Gravitinos have the same space-time chirality. And remember that the space-time chirality is imposed by the GSO projection. So this spinor has the same property of this spinor. So they come from different point of view from the worksheet. This one was coming from the right sector, this one from the left sector, but from the space-time point of view, these two spinors look the same. What if you want to get type 2a, which people calls n equal 1, 1, right? In that case, what you would need to do is to change the GSO projection, but only in the Ramon sector. So if in the Ramon sector you define, right, in this left Ramon sector, you define the GSO projection as keeping the states where the sum of the weight is odd instead of even, then you get the opposite chirality. So the index down represents the opposite chirality of the spinors. And so you see that now the second spinor is different from the first spinor. So the spinor coming from the Navier-Schwarz-Ramon tilde is different from the one that comes from Ramon-Navier-Schwarz tilde. Now you may say, okay, hang on a moment. Are you really allowed to change the GSO projection for the Ramon sector, right? I mentioned that we are not allowed to do so in the Navier-Schwarz sector. In the Navier-Schwarz sector, we have to choose the projection that kills the tachyon and keeps the vector. Otherwise, this argument with the 3-point function does not work. The answer is yes. I can change the GSO projection in the Ramon sector. And the reason for that is that Ramon states must always appear in pair in 3-point functions. And it's again just something that follows from the lattice description, right? The 3-point function is the sum, is related to the sum of the 3 lattice vectors representing the 3 states. And they can't have all half-integer weights. Right? So if you just take an example, right, you can have something like -1/2, -1/2, -1/2, -1/2, -1/2, -1/2. This is 1, 2, 3, 4, 5, 6. This is state 1. Then you can have -1/2, -1/2, -1/2, -1/2. Right? So this is a Ramon state, all plus 1 minus. This is another Ramon state where I flipped this sign, this sign, this sign, this sign. I flipped 4 signs. So this is still in the same GSO projection. Right? And you see that the third state has to be 0, 0, 0, 0, 1, -1. So I'm just saying that the sum of 2 half-integer numbers is integer. So in the 3-point function, this is something that is not obvious from supergravity. It's obvious from string theory. The 3-point functions are always made out of an even number of Ramon states. So you can check that in your favorite supergravity. You take the action. Type 2 are a bit complicated because there are Chern-Simons terms in the field strength. You expand. You can check that Ramon fields that have Ramon in either left or right or both, they always appear in pair. Since they always appear in pair, I can change chirality without any problem. So the freedom of choosing type 2b or type 2a is related to the freedom of changing the GSO projection in the Raman sector. And you just have 2 choices. Either you make the same choice for this guy and this guy, you make the same choice, and then you have type 2b. Or you make an opposite choice for this guy and this guy, and then you have type 2a. So you choose the left and the right, either they are equal or they are opposite. If they're equal, then you have a chiral theory in 10 dimensions. If they're opposite, you have a non-chiral theory in 10 dimensions. So the final bit of this calculation is when you pair Ramon, both from the left and the right, both for the holomorphic and the anti-holomorphic sector. So you have CS. So in type 2b, you will have, so this is 2b, -1/2 and tilde, SB -1/2 e to the ikx. Right, so in type 2b, the fourth sector, where you have Ramon both in the holomorphic and the anti-holomorphic sector, you see has a Spinor index for the left sector, a Spinor index for the right sector. So the object you have is a bispinor. It's something that has 2 Spinor indices. These are the Ramon fields. Now, how do you interpret these bispinors? Can I make them kind of more manifest, what that means? Well, that's just representation theory, right? And something you can do, and maybe the supergravity expert among you do this for a living, is taking this guy and doing a first expansion, right? So write this M, take this M, and write it in terms of a product of gamma functions. So let me not explain all the symbols, but just tell you. So you can always write this bispinor as sum. You basically, the gamma function and the product of the gamma function, these are the gamma function of SO1, 9, form a complete set. So you can take a matrix and write in terms of the constant, the one gamma function, the product of 2 gamma function, 3 gamma function, 4 gamma function, so on and so forth. So you see that this Raman sector contains a lot of forms, right? A lot of fields that have anti-symmetric indices. So they're a bit a generalization of this B mu nu. Now, the difference between type 2A and type 2B is that if these two indices have the same chirality, then this sum goes over only the number of objects that have a node, or the gammas that have a node number of indices. Right. So it will have one object with 1 index, an object with 3 indices, and an object with 5 indices, with 7 indices, and with 9 indices. Right. So let me zoom on this Raman sector and provide the final summary of the spectrum. So to be Ramon, you will have F mu, F M1, M2, M3, F M1, M2, M3, M4, M5. Right. So the fact that the even one are missing is related to the fact that these two have the same chirality. An object with an even number of gammas will be a matrix that is off diagonal in the Weil representation, changes chirality. So they cannot appear. So you have these fields. The other consequence of this object being chiral is that you can multiply it by gamma 11. Gamma 11 is the standard gamma 0, gamma 1. It's just the product, right? It's the chirality operator. You multiply by gamma 11, it doesn't change, right? Gamma 11 acting on a chiral field, a chiral spinor, gives back the same spinor. So you can take this object here, this M, multiplied by gamma 11, and it has to be the same. But then you can write gamma 11 explicitly as product of gamma. Right? So let me do it for this case. You have C gamma mu gamma 11. This is C gamma mu Fm Fm. Right? So I choose this one. This one is paired with just one single gamma. I can multiply by gamma 11, and I get the same thing. But then I can write this gamma 11 as gamma 0, gamma 1, gamma 9. And then you see that this product multiplied by this will just kill the gamma, because gamma squared is 1, and leave all the others. So here, if you have gamma 0, it will leave you with C gamma 1, 9. So this is why I stopped here. So this is telling me that the object with 7 indices and the object with 9 indices are not independent from the object with smaller number of indices. Again, the chirality condition tells you that they are related. So you might have seen this a bit with Dario's type 2B supergravity. Is this making a link? Did you see these Fs? No. Okay, then maybe you will see it, right? So what I'm just doing is that I'm constructing the spectrum of a theory. And then if you then say this is the massless spectrum, if you go to low energy, just that massless sector is the only thing that survives, and that will be the matter content of a supergravity theory where you write an action, right, just for these massless fields. And will be an action for a graviton, a B field, a dilaton, two gravitinos, and a bunch of anti-symmetric fields. What I'm telling you is in the type 2b, this bunch of the anti-symmetric fields are these three anti-symmetric fields. The fact they are only the odd ones, and I stop with this one, is because of the chirality condition. Both things are consequence of this chirality condition. This chirality condition tells me that F1 with one index is paired with F9, and that pairing is just the Hodge duality. Gamma 11 is implementing the Hodge duality. It's taking away, if you put m equals 0, it's taking away m equals 0 and is giving you all the others. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the condition on this field, and it's a bit subtle if you want to keep track of the signs, I will not do it, is that Fn, n is the degree of this antisymmetric tensor, is the Hodge dual of this is F tan minus n. And there are signs here. Right? But what is relevant for me is that F1 is paired with F9, F3 is paired with F7, and Fi is paired with itself. So if you want to describe the number of degrees of freedom, you say, I have this guy, and a self-dual object. An object that has only half of the degrees of freedom because it has to be equal to its own Hodge dual. So the type 2a, the Raman sector will just be the complement. It will just be something that has two indices and something that has four indices, and the others are related by Hodge duality. Right. So you see that the Ramon spectrum again changes, and the reason is because now this metric has opposite chirality. Right? These two indices have opposite chirality. I'm calling this field F, not by chance, but because if again you go back to this Q1, the constraints coming from the BRST charge, the Q1 part, you want to check that this object is physical. The condition that you will find are conditions that are like this. K slash, so it's the momentum with the gamma matrices, the standard K slash acting on M equal M, K slash equals 0. So this condition, if you write them, these are written in momentum space, if you write them in terms of derivatives, right? This K is like one derivative. You write them in terms of derivatives on this F, are the equation of motion of a U1 field strength, just Young-Mills. It's just funny because it has, in general, a larger number of indices. So I call them F just to recall that they are like field strengths. So these are a bunch of and this is the content of type 2a. Okay, any question? Very good. So we can breathe, and then in the final hour, I introduce the deep brain, and I do the calculation of the tension. Okay. Okay, so let me come to the open string sector. So we know how to perform to obtain the open string in the case of the bosonic theory. What we said, you just need to identify the anti-holomorphic and the holomorphic components, right? And the identification, if you go back at the very beginning of this course, what we did is to introduce identification metrics, like Rn, that in the case of the branes that are flat, the only case we consider was just a bunch of ones and a bunch of minus ones. This was related to the Neumann condition, and this is related to the Dirichlet condition. Right? And then we said that the alphas and the alpha tildes are related through this R. Right? So this contains the alpha tilde, this contains the alpha, right? And once you impose this relation on the boundary, right, it tells you that these objects are related. The alpha tildes, you don't need to specify them independently, right? They are just function of what you choose for the alpha. So the same thing will happen for the psi's, right? Because the psi's have the same index, right? So you can do the same thing for the psi's with the same metrics. And so it means that for the Navier-Schwarz sector, everything will work the same as the bosonic theory. Now the complication is what to do with the Raman sector. Now the states in the Raman sector right, have a Spinor index. Right? So how do I do the identification in that case for the Spinor indices? So the idea is similar to what the idea you follow when you derive for the first time Dirac equation. Right? So you want to find the same object in a different representation. So this is in a vector representation because it has vector indices. And now I want to find the same object in a Spinor representation, R Spinor. And then once I have an object that has Spinor indices, I can act on this S. And I can find an identification between the S tilde and the S. So how do you do the dictionary? Well, you use the gamma matrices. This is how you do for the Dirac field. So you say your gamma matrices have Spinor indices because they are a matrix in Spinor space and a vector index. And you say, if I act with this matrix on the vector index, I should get the same thing as acting on the Spinor indices. So this gives you what the representation of the identification matrix is in terms of Spinors. So this object is 1 when this index is in the Neumann direction. And is -1 when it's in the Dirichlet direction. So this guy has to be something that anti-commutes with the gamma if this index is Dirichlet, and commutes with the gamma if this index is in the Neumann. Right? And it will provide exactly these signs. And this is very easy to find, a solution of this. So you take the gammas for the Dirichlet direction, right? So these are gamma p plus 1, gamma p plus 2 times gamma 9 minus p. So these are the gammas of this bit. And you multiply each gamma by gamma 11. Now, this is a pair of gamma that commutes with any gamma that is not p plus 1, not p plus 2, and not 9 minus p. So any index which is along the Neumann direction, this object will commute, and then r minus 1, r is 1, and so this will be 1 if this index is Neumann. But this guy will anti-commute with the Dirichlet direction, so it will give a minus sign, and that's the minus sign here. So this is an explicit representation of the reflection matrices on the gammas. And so the description of open string starting and ending on a D-brane in type 2 theory requires that S tilde is identified with this reflection matrix times S. So this is the Spinor version of this. Well, this R is R Spinor. Now, it's not obvious you can do that, right? Because this guy should have the same chirality as this guy at the end. And so, if you check, you will see that in type 2A and type 2B, where these two objects have opposite chirality, right? S tilde and S have opposite chirality in type 2A and the same chirality in type 2B. In order for this identification to be possible, right, the number of space-like Neumann direction has to be odd for type 2B and even for type A. So while in bosonic theory you can have D-branes of any dimensionality, right? In the superstring you have p-branes of odd dimensionality in type 2B and even dimensionality in type 2A. This is just a consequence of the fact that if you multiply an odd number of this object, this changes chirality. If you multiply an even number, it doesn't, right? And so one case is possible for type 2B, where S tilde and S are the same, and the other case is possible only for type 2A, where S tilde is opposite than S. So what I'm saying is that all the constraints that you can see from kind of a low energy description, here from the worksheet description, you derive them. Now, one interesting case, which is I think the case that you are focusing on a DSCFT, is that of D3 branes. Now, as we mentioned, this breaks the Lorentz group, so the presence of one D3 brane, or for that matter, of many D3 branes that are exactly the parallel. So these D3 branes are extended in time, of course, and in direction 1, 2, and 3. Right? These are the Neumann directions. So this block of the matrix is 4 by 4, and this block of the matrix is 6 by 6. Yeah? Yeah, so the GSO projection is telling that you are just choosing half of the states here and half of the states here. But that GSO projection is nothing else than the chirality. right? So it's choosing the object that sum to even. It means like gamma 11 is even, and choosing the one that sum to odd is gamma 11 is odd. So this comment that I said here, the chirality forces you to have in type 2b to be odd and type 2a to be even, is just a rephrasement of what you are saying. The chirality is the same as the GSO. More questions? So in this case, you just focus on the holomorphic part. The anti-holomorphic part is determined, right, by this relation and this relation. And the holomorphic part contains a Navier-Schwarz sector, and this Navier-Schwarz sector contains a vector right. So this is the massless state psi e to the minus phi e to the ikx, the rest with c. And this index mu goes from 0 to 3, so this is a vector. And then you have 6 scalar. So vector and 6 scalars. Well, now I discuss vector and scalars with respect to this Lorentz group. Right? The Lorentz group that the open string C. And the 6 scalars looks like this, but now with the index along the Dirichlet direction. So this is the Navier-Schwarz sector. And the Ramon sector, well, the Ramon sector, you still have the same structure as here, just the holomorphic part. So you will have CSA minus 1/2 e to the minus phi over 2 e to the ikx. That's the Ramon sector. These are still 16 states, right? This A GSO projected has 16 possibilities. So you just have to do, again, representation theory. Don't want to enter too much into this. So you want to take this 16-dimensional representation of SO1, 9 and decompose it into irreducible representation of this subgroup. And what you will get is 4 gauginos, so 4 spin 1/2 object, that have a Spinor index of this SO6. So in the language that I was writing, so in this language of e to the I plus or minus 1/2 h1 plus or minus 1/2 h2, etc., e to the minus phi over 2, it's very intuitive because saying 4 dimension, you're just taking h1, h2, right? These are your 4 psi 0, psi 1, psi 2, plus I psi 3. And this will be the transverse one. So you see explicitly that this is a Spinor here, but it's also a Spinor here. So that's why the Ramon sector gives gauginos, and gives gauginos that have a flavor index, how they transform under this object. But it's not a fundamental representation of SO6, but it's a Spinor representation of SO6. It's just because these are all half integer. So this is the content of n equal 4 Super-Yang-Mills. 1 vector, 6 scalar, and 4 gauginos. Very good. Okay, so in the remaining time, I will sketch the only one loop calculation that has a very important physical meaning and will provide us with some physical information of the DP branes. So let me first motivate why we do this calculation, and then I will just highlight what the steps are, writing some results at the end. Unfortunately, I will not be able to give you the derivation. So once you have this spectrum, right, type 2B theories, right? So the observation and the puzzle people had for a long time is that the perturbative spectrum that you obtain here has a lot of U1 fields, but they appear through their field strength. So the perturbative spectrum appears directly through the field strength. So this tells you immediately that there is no perturbative state that is minimally coupled to this U1. What is the minimal coupling? Well, think about QED. The minimal coupling is A mu J mu, right? So if you have an electron, right, this charge, an electron that doesn't move, right, it will produce an A0. Here, you always have derivatives. So if you have you don't have any 3-point coupling where you have one object, and just the gauge potential. Because all the 3-point couplings that you can write with these perturbative states involve directly the field strength, and so this coupling would go to 0 when k goes to 0. This coupling does not go to 0 when k goes to 0. So theorem, there is no perturbative state that is minimally coupled to these U1s. But what people knew from supergravity was that if you write the supergravity action of all these fields, and you focus on the bosonic field, right? So you focus on the Ramon, and the Knavish sector. You can write classical solutions of these equations that represent some object in space-time. And those solutions were electric solution for the gauge fields, or even magnetic, right, thanks to this duality, for this gauge field corresponding to this F. So it's a bit like the electric field for the Coulomb charge, right? People would write a solution that had a non-trivial metric, a non-trivial dilaton in general, and then a non-trivial gauge form, where the non-trivial gauge form is for the gauge potential of these guys. According to the comment I just made, this cannot be any perturbative state in the string theory. You may think maybe it's a very massive state. A very massive state creates some curvature in space, right? It cannot be, because it's not minimally coupled to the gauge field. So there was a long-standing issue: are these states present in string theory, or maybe just something that comes from supergravity? And I think, did Dario introduce this classical solution for the D3 brane? The one with the, I don't know, maybe we'll do next week, with the harmonic form 1 plus, right? You have done that, right? So basically, if you think this harmonic form will give you an explicit form for the metric, an explicit form for this guy, but it will give you an explicit form for this guy for the potential, and it will be minimally coupled. So it will be like an extended electron. It will have a charge density minimally coupled to the gauge potential of this guy. So the question is, where are these states? Are they in string theory? So the intuition of Polchinski is that these states are the DP brane. So message, DP branes are minimally coupled to A, where F is the A. And this F is the Ramon field strength, and this A is the Ramon gauge potential. Not only that, but he was able, and I will just sketch briefly what the idea is, to calculate what this charge is. Of course, being this object extended, this is not really a charge, it's a charge density. Right? It's a charge which is spread around the whole board volume. So Polchinski calculated also the charge density and the tension, which is the energy density. What does it mean? Calculate is telling you that the coefficient in that h that you found, h is 1 plus some coefficient here divided r to the fourth for the D3 brane, right? That object that is here, this is related to, is a bit like a Schwarzschild solution, right? You go for very large r, this guy knows about the mass, right? If you do Reisen-Nostrom, knows about the charge, right? So this guy knows about the mass and the charge. From the supergravity point of view, you can put anything, right? All of them will be solutions. But in string theory, this object, this quantity is fixed. And this is what he calculated. So let me write the result of that, because that's an important result. And it gives you a flavor of how it looks like. So the tension, let me call it TP, is equal to root pi K10 2 pi root alpha prime 3 minus P, where K10 is related to the Newton constant, so it's just 1 over 2 K10 square root of GR plus dot dot dot, right? So that's how I think you normalize your supergravity action. I think that's kind of standard. So you see, this is telling you that the tension of the string is complete, the tension of the D brane, sorry, is completely determined by string theory. And then you can write the charge density. The charge density, let me stress, is the charge with the Ramon field. And the Ramon field, the branes coupled to, is AP plus 1. So it's a field that has P plus 1 indices. And these P plus 1 indices are exactly those of the board volume. So think about the case P equals 0. That's like a point-like object. The point-like object is charged under a gauge field with one index. The electron is charged under A mu. And the minimal coupling produces A0, which is the electric potential. So this is a generalization of that. The minimal coupling produces the A with 0, 1, 2, 3, 4, up to P. And then you can check if P is odd for type 2B, P plus 1 is even, and the exterior derivative of P plus 1 is P plus 2, is again odd, and that's what you had. Right. So the D3 brane, the case where P is 3, you have 3 spatial direction. It is charged under a 4 form, gauge potential, which has the indices along the board volume, 0, 1, 2, and 3. And the field strength of this 4-form gauge potential is a 5-form field strength, which is exactly this self-dual object. So this charge mu p is a charge under this field, and the form it takes is this. where the kinetic term of this phi form is normalized in the standard way. I mean, you need always to, I mean, these are a bit, you need to be careful, right? Because, of course, in the minimal coupling, right, the minimal coupling would be this. That would be the minimal coupling on the work volume of the D brane. So dp plus 1 psi. That's the minimal coupling. You can say, okay, I can change the charge here just multiplying A by any factor, right? I rescale A by a factor of 3, I change the charge. But no, when people talk about the charge is when the gauge field is canonically normalized. So the propagator is just 1 over k square, right? If you rescale this guy, you will change this normalization here. So the idea is look at a canonically normalized object, right? Where the propagator is like the photon, it's 1 over k square. That fixes the normalization, and that fixes the charge. Now this number you cannot. So the observation Polchinski gave is very nice, is that if you take this explicit result, and if you do mp times m6 minus p, that's equal to 2 pi. Right? Because this exponent will flip sign, so it will cancel, and so you will get root 2 pi twice. Now, why is this interesting? This is interesting because this guy is charged under Fp plus 2, right? Minimally charged with Ap plus 1, and the field strength is Fp plus 2. And this guy is minimally charged with 7 minus p, with 8 minus p. Now, this guy and this guy, for the discussion we had before, are Hodge dual. You see, 8 minus p plus p minus 2 is 10. So you can think about D0, D1, D2 brane as electrically charged, and D4, D5, D6 as magnetically charged under the forms with small number of indices. So basically you can think about a D6 brane as magnetically charged under the electric field of the D0 brane. And this is Dirac condition, right? So Dirac conditions is telling you that in a theory you can have an electric and a magnetically charged object only if the product of the charges is a multiple integer of 2 pi. So the condition would be this condition with a factor of n. Any integer would go. But if you find the case with n equal 1, then you know that these are the objects with the minimal charge. You cannot have any other object that has charge smaller than this one, right? Because suppose that you find m0 and a m6 hat that has half of the charge of m6, you will spoil this, right? You will get pi. Because m0, m6 gives 2 pi. If this is half of that, it will give pi. So he said, okay, not only I find objects that are minimally coupled to the Ramon field, but these are the elementary objects. I don't have any object that has smaller charge than this. Very good. Any question on the philosophy? Very good. Very good. Very good. So let me just pick up on this question. So you now have this object right? And for the time being, we have been thinking about this object as a static object that has p+1 direction that are Neumann, and then the orthogonal direction. Now you can say, let me make contact with the very beginning of this lecture when we try to write action, very beginning of the course, when we try to write action for extended object. And I said, well, a natural action is kind of a generalization of the Nambu-Goto action, right? So you take the metric of space-time and you do the pullback. So you would say that action should be the effective action of this extended object, right? That's the minimal thing. So you can write, now seen as an effective dp brane action, you would expect something that is dp plus 1 psi root of the determinant of G, right? So this object here, you see, being the pullback, will depend on the shape of the brane. So if the brane is straight, okay, this will be a number, but then you can start fluctuating the brane a bit, and you can expand this in what is called static gauge. It will give you an effective theory. So this bit we expect, and is related to the scalars here of the open string. There will be an extra e to the minus phi in the dilaton. And then, as you said, there is a new term in the effective action, which is exactly that one. So this guy will come with a tension, and this tension is that number. So we calculate it, right, from fundamental theory. And then there will be mu p AP plus 1. And then again, you can think about this as the pullback of the space-time Ramon field on the brane. And so you can start, so this is kind of an effective action that we can start expanding what if the brane vibrates. So we can derive this quantity and this quantity. And of course, you can also derive more terms in the effective action by doing open string amplitude. That's one way. More questions? Okay, so let me just sketch the derivation and stress one point that is important in the derivation. So it's a daunting task because you want to do a calculation where all the factor of 2 and pi's are kept under control, right? Otherwise, if you do something wrong, you will not get this Dirac condition, and then you say, okay, maybe these objects do not exist or not me. So it's a calculation where you need to get all the factor of 2 and pi's. So what is the starting point where you don't have any doubt about the overall normalization, right? So that's, you need something, you start from a formula where you say, okay, I have no doubt of what this formula is. So what Polchinski starts thinking about is a situation where you have two DP branes, then you have open string stretch between the two DP branes, right? And then from the word volume point of view, it means that you have a disk, right? And this disk, you have sigma equals 0, sigma equal pi, right? This is the, z equals 0, z equal infinity, and this is the sigma equals 0 boundary, and this is the sigma equal pi boundary. So this is just this picture, right? 0, upper half plane, right? One boundary, the other boundary. So what it thought, it said, well, if I want to calculate the interaction between these two DP brane, and this DP brane, I want them not excited. I want them in the lowest possible state because I just want to calculate the tension. I don't want to calculate the tension plus some extra energy on the top. Right? I don't want any open string insertion. Right? The open string insertion are excitation of these d branes. So what he says is that, well, then I want to get rid of these points. I don't want to have an insertion. But I still need to have the boundary staying on the same, the endpoint staying on the same boundary. So the simplest possible calculation I can do is a calculation like this one, where this stays on one d brane 1, and this stays on the d brane 2. So the idea is you take this open string and you make a loop. If you take this open string and you make a loop, then this is one boundary, and this is the other boundary. So that's why it's a one-loop calculation. And the idea is that this one-loop calculation provides you with the effective potential. Now, this is very familiar in QFT, right? You can take a scalar theory, and you can calculate the one-loop potential, like Coleman-Weinberg, just by doing one-loop calculation. And the formula that people use in field theory is nothing else than just doing the Gaussian approximation of the path integral, and is often written in this form. So let me write in. So P is the propagator. So P is the bit that knows about the quadratic fluctuation of your field theory. So it's the quadratic term of the field theory, the propagator. And so the idea is that you take log of the propagator and you sum over all possible states, multiplied by -1/2. This -1/2, this is just a rephrasement of saying that the one-loop calculation gives you one of the determinant of the propagator. So I realize that I'm not giving a kind of complete derivation, right? Clear derivation. But I just want to mention two things, is that this formula is the same formula used in quantum field theory when you do the Coleman-Weinberg potential. It's nothing new. And this numerical coefficient is fixed. And it's fixed just because you are doing a Gaussian integral. And this 1/2 is just the square root that you get from a Gaussian integral. So this is the starting point that Polchinski used. Said, okay, this is a potential, so something that tells me what the interaction of this is. And that potential is determined by a formula that I know exactly. I don't have any doubt about this normalization. So this was the starting point. And the calculation is done by taking over this trace the sum over all open string states. So it has the same flavor, and technically is exactly the same as the calculation that I did when I found for you the asymptotic degeneration of the Bosonic string states, right? And I found this exponential behavior with the Hagedorn temperature. That's the very similar thing. So when you sum over all string states, this trace will be over the states generated by the alphas in the X. There will be a contribution coming from the states generated by the psi's, a states generated by the BC, a states generated by the beta gamma, right? So you sum over all the possible states in your Hilbert space. And you get a result, and that result is expressed in terms of an integral. And so tau That's a result. So that integral, I want to explain to you what this integration parameter is. So if you look at this worksheet picture, it seems that you have two parameters that you can play with. Right? It seems you can play with the width. Right? You can have different looking surfaces because the hole is smaller and bigger. Or you can play with this length. You can keep the width fixed and just making a bigger loop. But what I'm saying is that this is misleading, because when you think in this way, you are thinking about a situation that is not conformal. Right? In a conformal theory, the information about the area is not important. Right? You can rescale. And all our theory here are conformal. So the only real parameter that you are left with is the ratio of these two lengths. The ratio of this guy and this guy. That ratio is a conformal invariant quantity, right? If you rescale your metric, it doesn't change. So that ratio is tau. So let me call this tau open. And think about tau open as the ratio of this guy divided by this one. So length divided by width. So it's natural that this result will be expressed as a sum over all possible worksheet you can have. So what I wanted to do, but that will require another hour, sorry for that, is to give you an explicit expression for this. You have all the technologies, just traces over the CFTs. But the explicit expression, okay, you can calculate by yourself, so let me just focus on the conceptual bit. Now, what are the extreme of integration here? Well, from 0 to infinity, right? That's all possible conformal invariant object. Now, the fact that this goes from 0 to infinity seems a bit problematic, because it looks like you still have UV divergences, right? You can make this thing very, very, right? You can make this length super small. So Polchinski's idea was, well, we actually have another viewpoint where that is more useful to describe the case when tau is very small. So when this tau is very small, it's better to introduce another parameter that I call tau close, which is just the inverse of that. What does it mean? Well, it means that I am taking the inverse. Tau close is the ratio of the width divided by the length. Right. So I am swapping the role of these two directions. So if in this picture I was thinking about this direction as the time evolution direction, and this direction as the space, so this is the time evolution and the space, so I see this as an open string that does one loop, as I would do in normal quantum field theory, right? In this picture, tau close, where I exchange the role of length and width, I write it in terms of width divided by length. So what it means is that I'm now thinking about this direction as time and this direction as space. So what I'm doing is I'm thinking about a closed string, because this direction is space and you see it's closed. This is the space direction at another time, still closed. So I see this picture as a closed string starting from this boundary and propagating up to the other boundary. So you see this in this form. So this is a very different physical interpretation, but from the mathematical point of view, it's just a change of variables. Once you have this explicit expression, you just have to do a change of variable. And you get a new form of the same answer that goes again from 0 to infinity of a new expression. So this is an expression of tau open, this is expression of tau closed. Right? Where now this infinity corresponds to this 0. So a very, very tiny annulus corresponds to a very, very long cylinder. Now, from this point of view, you start making connection with this quantity of charge and tension, right? Because the Polchinski idea is that if you make this cylinder longer and longer, right, then you can start separating the contribution of the different string states, and these are closed string states that propagate. So you can have the leading contribution, which is due to the massless states. Those are the long-range forces. And then you have massive states that have Yukawa-type forces that are more and more suppressed if you move the brane far apart. So what he did is take this expression here, expand this expression for large tau close, take the leading term of that expression, and separate the contribution that comes from the Knavish-Worth sector from the one that comes from the Ramon sector. Just because in the calculation you can follow these two contributions completely separately. So if you focus on the Knavish-Worth contribution here, then you would like to match that result at large distances with the exchange of graviton, dilaton, and B mu nu. Right. You will see that B mu nu does not appear, and in general, graviton and dilaton are the only one that contributes. If you look at the Ramon bit, these are really sum of terms. Right? So you look at the Ramon bit, you do the same expansion far away, and you will find a contribution due to the Ramon states. Now, the number that you find there is basically the square of the tension in the Knavish-Worth case and the square of the charge in the Ramon. Why the square? Well, because you have two of them. Right? So it's really like the Coulomb force. Right? I have the potential is one charge times the other. So if I focus on the Ramon sector, I match this result from string theory at large distances just with the Coulomb law. And if I focus on the Knavish-Worth sector, then I match it with the interaction to the graviton and dilaton. And in that way, you find these results. Okay, any questions? Okay, maybe can I take 3 more minutes? So I want to make 2 remarks that are one more stringy and one more ADS-CFT. So sorry for taking this, but I think these are important points which might be useful for you. So the first remark I want to make is that you can take this result and cut one of the sources. Right? So once you have this result, you literally identified this result as a D-brane that emits a graviton. This graviton propagates and is absorbed by the other D-brane. each of these coupling is proportional to the tension, right? You can just erase one of these sources, right, from the result and find the result for this guy, right, where this propagates. This result here is telling you that the brane is producing a non-trivial gravitational field and is producing a non-trivial Ramon field. Right, so this is a diagrammatic version of how the Coulomb field is produced and how the gravitational field is produced. So this is telling you that this solution that Dario brought for you, you can start seeing this solution in the large distance expansion, literally as emission of graviton, as emission of Ramon field, emission of dilaton coming from a physical source. So the brane, being a physical object with a tension, it does curve space. And being a physical object with a charge, it produces an electromagnetic field, a Ramon field. So this is the first observation. And it's this link that Maldacena used, right? So this idea that these branes, and I think this is what Dario was one of the starting points for this at the SCFT derivation, the fact that this D3 brane, you can see them as the objects supporting open strings, and these open strings are, at low energies, the excitation of n=4 super-Young mills. So that's one picture you have of the branes, and we have been constructing that super explicitly, right? So you know the spectrum, you know the interaction, you can calculate that this really fills the action of n=4 super-Young mills. Or a bit more sketchy here, I was telling you, you can see the branes as the source of a gravitational back reaction. So you can see these branes through the effect they have on the background, curving the space and creating an electromagnetic field. But it's the same object. That's what Maldacena used to get to the first ADS-CFT duality. The second observation that I want to make is that this duality, right, between the annulus and the cylinder is telling me that what looked like a ultraviolet divergence in one channel, something that became very, very small, it actually is nothing else than an infrared divergence in the clustering channel. So when people say string theory is free of UV divergences, this is one of the mechanisms you have. Right? So you can have something that looks like a UV divergence, but then when you go to the right variable, you see that it's nothing else than the propagation of an almost on-shell state for a long time. And here the propagation, when this tau open is very, very small, the propagation of the almost on-shell state is a clustering on-shell state. It's just telling you that the kind of better picture is not of a very, very small annulus, but is of very, very long cylinder. And that clustering is propagating for a long time. So this is one half of the story, and the other half of the story is clustering amplitude, right? So where you don't have this open-closed duality, right? You just have clustering, so you have kind of a loop amplitude which is a torus instead of being something with boundaries. In those cases, you do not have UV divergences because the equivalent integral does not go till 0. So string theory will cut the UV part with an alpha prime bit, will cut it out, and so that's the other mechanism string theory uses. And when you combine these two mechanisms, you can see that intuitively they are very general. You can have a complicated surface with boundaries and many handles, but for each one of these two mechanisms is at play. So that's why string theory provides, an intuitive motivation, that why string theory provides a finite theory of a finite perturbation theory, including gravity. Okay, sorry for being late, I stop here.